So what is hydrogen? I think everyone knows about the hydrogen. So what is hydrogen? It is the lightest element we are going to have in a periodic table. So that is the one point we can able to say. So what are the electronic configuration of hydrogen? It is going to be 1s1. So which is the simplest element we are going to have in periodic table is hydrogen. So what it is going to be? The lightest element. And if you are taking electronic configuration, 1H1 we are going to represent, and it is going to show 1s1 electronic configuration. This electronic configuration of hydrogen is going to be making it very peculiar in its position. So first and all, what the problem we are having with hydrogen? That is, the problem is position of hydrogen. So where I have to place the hydrogen in periodic table? So that is the first problem we are going to have, is the position of hydrogen. So what are the periodic tables we are having? The first periodic classification is given by Mendeleev. Mendeleev has given its first periodic table. What is the law of Mendeleev? The Mendeleev has suggested that the periodicity is a function of their atomic masses, and he has given 63 elements classified, and he has given the tabular form first time, and he is not able to place the hydrogen in a proper place. That's what we are discussing. The demerit of Mendeleev is the hydrogen can't be placed, and even more they are having anomalous space and so many things are there. So that is irrespective of our discussion now, but the Mendeleev has not given the proper place for the hydrogen. And the next one, Moseley. Moseley has given its periodic table, which is going to be called as modern periodic table. What the law he has given? Modern periodic law. What is modern periodic law? The periodicity. What is the meaning of periodicity? The properties which are going to have similarities at a regular interval is called as periodicity. That periodicity is the function of atomic number. Moseley has arranged all the elements in increasing of atomic number, and in that increasing of atomic number, then he has placed the elements. He has successfully placed all of them into 18 groups and 7 periods, but he also not able to give a proper place for your hydrogen. The Moseley also not able to give a proper place for hydrogen. And the next one, the long form periodic table. So what periodic table nowadays we are using all the way? We are using long form periodic table, which is given by Niels Bohr. Who has given this one? Niels Bohr has given its long form periodic table. According to him, the periodicity is a function of electronic configuration. Periodicity is a function of electronic configuration. Now, he arranged all the elements in increasing order of electrons, and he has constructed the periodic table and 18 groups what we are using now, and the 7 periods as we are discussing now. The what are the periodic table we are following? That is the long form periodic table, which is constructed based on electronic configuration. But that electronic configuration based periodic table also not able to give a proper position for your hydrogen. Proper position for your hydrogen. Why it is not able to give proper position for hydrogen? That is what you are supposed to see. Why? Because the hydrogen is going to have the similarities with alkali metals, and it is also having the similarities with halogens. What the problem we are having? Because to give position, what the way we have classified the periodic table, whichever elements are showing the similarities, they have kept in one group, and which of them are showing some regular intervals, they are going to show the periodic properties. So like that we have arranged. So in order to place hydrogen, what are the things we are supposed to consider? We are supposed to consider that hydrogen is showing the similarity with which elements that we are supposed to take, and that one we are supposed to group the hydrogen into it's a group or a period. Now, when we are going to take the hydrogen, where we are going to have this one? It is going to be present in first period. Placing the hydrogen in a period, we are not having any problem. Why? Because periods are meant for the filling up of electrons in a shell. So they are going to have one shell. So in its period, we are going to have hydrogen and helium. Both of them are present. That's why we are not having any problem. 1s1 is the hydrogen, 1s2 is the helium. That's why we will not have any problem to place the hydrogen in first period. But now we have to place it in a group. Which group I have to place the hydrogen? In which group I have to place the hydrogen? Whether it has to place in a first group or whether it has to place in a 17th group according to Arabic number. Otherwise, according to Mendeleev, it's going to be a 7A group, the halogens. Why? Because it is going to have similarities with alkali metals. It is also having the similarities with halogens. So that is what we are having. The problem is alkali metals we can able to say 1A group or Arabic number if you are saying first group. Halogens if you are going to say is according to Mendeleev it is going to be 7A group. According to the recent long form period table it is going to be 17th group. Understand? So what we are discussing now? The position of hydrogen. Where I have to place the hydrogen? Hydrogen, if I want to place it in a first period, I am not having any problem because the electrons are going to be filled up in a first shell. So that's why there is no issue with where I am going to place the hydrogen in a period. So first period definitely we can able to keep. But the next one what you are going to have the problem? Which group I have to place the hydrogen? If I want to place the hydrogen, I have to check the similarities of hydrogen. Now first if I am going to see, it can able to show the similarities with alkali metals and also it is showing the similarities with halogens. So now where I have to place? That's the problem. First we will see what are the similarities we are having with alkali metals. What are the similarities? The hydrogen is showing the alkali metals. Now when I am going to see the similarities, first similarity, the electronic configuration. First similarity with alkali metals is electronic configuration. What is the electronic configuration of our alkali metals? First I am going to take lithium. What is the electronic configuration? 1s2, 2s1. So this is what we are going to have, the electronic configuration of lithium 1s2, 2s1. If I am taking the next alkali metal sodium 1s2, 2s2, 2p6, 3s1. So it is going to be the electronic configuration of your sodium. If I am going to take, next one is potassium. If I am taking potassium, so instead of keeping, I am taking the argon. Is going to have 4s1. Now the electronic configuration of lithium is 1s2, 2s1. For sodium it is 1s2, 2s2, 2p6, 3s1. For potassium it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That means every element in your alkali metals, they are going to show the last, what is the electronic configuration? 2s1, 3s1, 4s1. And what is the electronic configuration of hydrogen? I said 1s1. That means NS1, if you are going to take the general electronic configuration, what is going to be happen here? The hydrogen also showing NS1, like the valence shell is going to have only one electron in their outermost shell, and the lithium, sodium, potassium, rubidium, cesium, francium of your all alkali metals group is also showing same electronic configuration. So what the point I am saying now? The electronic configuration, if you want to see, the electronic configuration of all your alkali metals is going to have NS1 in its outermost shell, and as it is, if you are going to see, the hydrogen also is going to have same electronic configuration like NS1 only. So according to the electronic configuration, if you want to see, we can able to place your hydrogen element along with your alkali metals. Understand? So now we will see the next similarity what you are going to have. So the next character which is going to be the similarity with alkali metal. First one is electronic configuration, that already we discussed. The next one is electropositive character. The next one is going to be electropositive character. When we are going to take electropositive character, all your alkali metals, lithium is readily going to form Li plus electron, and next we are taking sodium Na plus electron, potassium if you are taking K plus electron. So that means all your alkali metals are going to be formed unipositive. They are readily existing in a form of positively charged, unipositively charged ions. Similarly, your hydrogen is also going to be present in the form of H plus electron. That means how alkali metals are going to show the unipositive character. They are readily forming the cation. So the same way the cations are going to be formed. So the same way I am going to get hydrogen also is going to show the positively charged character. That is unipositive charged ions are going to be formed. So that is the reason we are going to have the similarity with your alkali metal. Is it clear? Now when we are going to take the next comparison, oxidation state. So what is the oxidation state shown by your hydrogen? +1. All your alkali metals will be showing +1. So oxidation state of your all alkali metals is showing to the +1, and all your hydrogen is also going to show +1 oxidation state. Where you can able to see oxidation state, say for example LiCl or NaCl. Similarly, your hydrogen is also going to form H2O. It is also showing +1. HCl. It is also showing +1. So the oxidation state of your hydrogen is also showing +1, and along with your alkali metals, Li, here also it will be showing +1. Here sodium also will be showing +1. So as they are showing the +1 oxidation state, your hydrogen in this case, and in this case it is showing the +1 oxidation state. So the +1 oxidation state is also having the similarity with your alkali metals, and the reactivity when you are going to take. When we are going to take reactivity. So what are the reactions we can able to get to know? So when we are going to take lithium is going to form the chlorides, we are going to have lithium chloride, sodium chloride. Hydrogen is also going to form hydrogen chloride. Say for example, with halogens we can able to get NaCl, hydrogen will form HCl. With oxygen, if you are going to take, it will form Na2O, where hydrogen is going to form H2O. And similarly, when you are going to take sulfur, so it is going to form sodium sulfide, and hydrogen is going to form hydrogen sulfide. So when we are going to take the reactivity also, we are having how the alkali metal is going to form chlorine, sodium chloride, unipositive, and here also we are going to get HCl. Where you are taking the with oxygen, we are going to get Na2O. It is going to form H2O. Where it is going to form the sulfur, it is going to form Na2S, and it is going to form H2S. So these are all the similarities are making a clear intention that the hydrogen should be placed along with your alkali metals. Isn't it? First we discussed regarding the electronic configuration. Electronic configuration is going to be NS1, which is similar to your alkali metals, like same way we are going to have hydrogen. And the next one we discussed regarding the electropositive character. So the electropositive character means they are going to form uni-charged positively cations. So the same cations are going to be formed by your alkali metals also, as well as your hydrogen also. And then we discussed regarding the oxidation state. Oxidation state of your hydrogen is also going to be the +1, and the remaining alkali metals also is going to be the +1. Next we are going to take the reactivity. Okay. Huh? Okay. So reactivity, when you are going to take chlorine, NaCl, HCl, with oxygen you are going to take Na2O and H2O. And when you are going to take sulfur, Na2S is going to be formed and H2S is going to be formed. So reactivity is also going to be the similar one when we are going to take. So this is the reason we can able to be placing your hydrogen along with your alkali metals. And what are the factors which are going to be making the hydrogen should not keep with your alkali metals? Now we'll see what are the differences the hydrogen will be showing with your alkali metals. Understand everyone? So this is what we are having similarities. Now we are going to discuss the differences what we are going to have with your alkali metals. ఏమైనా క్వెరీస్ ఉన్నాయా రాహుల్ గారు? ఏమైనా క్వెరీస్ ఉన్నాయా? అంటే ఏమైనా పెట్టారా స్టూడెంట్స్ ఏమన్నా? ఇదే నాకు కనిపించలేదేనా? సో ఇక్కడ వరకునే రాయాలి అంతే కదా? కొంతమంది Actually, one more we are having is reducing ability. One more similarity is there, reducing ability. So what is the reducing ability meaning? All your alkali metals are having highly reducing nature, isn't it? All your alkali metals we are going to be discussing, they are going to show high reducing ability. So that metal usually we are going to show. Here hydrogen is also having the same reducing ability. Say for example, Fe3O4 plus H2. When you are going to take, it is going to be forming so the iron oxide, it is going to be get converted to iron. So it is completely reduced to its iron metallic form by your hydrogen. So that's what you can able to see it from this one. Same reducing ability we can able to see from your all alkali metals, isn't it? Everywhere you are going to have Na plus HCl. We are going to get NaCl plus H2 gas is going to be liberated. And we are having all alkali metals are going to show high reducing ability, that we will be knowing it, and the same reducing ability will be shown by your hydrogen. This is also going to be the similarity which is shown by your alkali metal with hydrogen. And now coming to the differences. So what differences we can able to observe? So the first and foremost is going to be the existence of H plus. How the H plus is going to be existing? All your alkali metal ions are going to be existing very stable. Li plus is stable, Na plus is stable, all your K plus is stable, everything is going to be stable. But how this H plus is going to be existing? What will be the H plus size we are going to expect? Usually when we are going to take atomic, least atomic size is going to be around 50 picometer. But this is going to have 1.5 into 10 power minus 3 picometer. The size of your H plus ion is going to be 1.5 into 10 power minus 3 picometer, which is not at all going to be possible to exist. Why? Because the normal least atomic size or least ionic size we are going to have is 50 picometer and 200 picometer. So this is what the size we are having for a least atomic size and least ionic size. That is going to be 50 picometer to 200 picometer. So that 50 to 200 picometer is not going to be possible for the H plus. H plus means we are going to have no electron in it, and we are going to have the size is going to be approximately 1.5 into 10 power minus 3 picometer. That much lesser size ion will not be able to exist. That's why whenever we are going to show H plus, this is always going to be existing as H9O4 plus. In water, it is going to be existing as H9O4 plus. That's what we are simply representing as H3O plus. Hydronium ion, we are representing H3O plus. Originally, it is not going to be existing as like this. It's going to be existing as tetrameric. 4 water molecules will be get tetramerized. That is going to be get up one H plus, so that C4 into H2O, H8O4, that is added up with one H plus, that is going to be H9O4 plus. So that is what simply are representing as H3O plus hydronium ion. But when we are going to take all your alkali metal ions, Li plus or Na plus or whatever the ions we are going to have, they are going to be acting as hexahydrated cations. They are going to be existing as hydrated cations. That too, 6 water molecules are going to be taken up and they are going to be existing as stable. they are going to be existing as stable ions, hexahydrated. But here it is going to be existing as hydronium ion. So this is the difference we can able to see. The existence of positively charged ion is not going to be possible with hydrogen because of its very small size. 1.5 into 10 power minus 3 picometer size is going to be very small. So that much size cation is not existing, but whereas alkali metal cations are going to be existing. So this is always existing as H9O4 plus, which we are simply representing as H3O plus cation, hydronium ion. So this is the first difference we can able to discuss with an alkali metal. And the next difference what you are going to have with your alkali metal, the nature of halides when you are going to take. The nature of halides when you are going to take. Say for example, the next difference is going to be nature of halide. When you are going to take nature of halide, HCl I will take, NaCl I will take. What is the nature of HCl? It's a covalent. What is the nature of NaCl? It's going to be ionic. It is going to be ionic. I think everyone knows about this one. HCl is going to be existing as covalent nature, and NaCl is going to have an ionic salt. And when we are going to take HCl, it is going to be existing in gaseous state, whereas NaCl is existing in solid state. It is existing in solid state. So the nature of halides which are formed by hydrogen, nature of halides which are formed by alkali metals, they are going to show differences in their nature. One is going to be covalent in nature, another one is going to be ionic in nature, whereas the HCl is going to be existing in gaseous state. Everyone knows it, I think, the volatility of HCl. We are existing in volatile nature, so that's why it is going to be immediately vaporizes. But when we are going to take in aqueous solution only, we are going to form the hydrogen bonding, that's why it is going to be existing in a liquid state. Whereas this NaCl is going to be existing in solid state. Use crystalline structure, rock salt structure we are going to have for NaCl. So that's why we can't able to keep with alkali metals the hydrogen because of these reasons we can able to see it. So what the things we discussed for your hydrogen? So alkali metals differences we have seen, and alkali metals similarities we have seen. What are the similarities we are having with your alkali metals? The first one is going to be the electronic configuration. They are having NS1 electronic configuration. Your hydrogen is also having 1s1 electronic configuration. Whereas the second point what we discussed, the oxidation state is going to be the +1 for your alkali metals. Your hydrogen is also showing the +1 oxidation state. And electropositive character, your hydrogen is going to form the positively charged cation, that is unique positively charged cation, whereas your alkali metals also going to form positively charged cation. Whereas the next character we discuss is reducing ability. So what is the reducing ability? So your all alkali metals are showing highest reducing ability. They are acting as reducing agents, whereas your hydrogen is also going to be acting as reducing agent. I have shown example here Fe3O4. Even cupric oxide also is going to be get reduced to copper by your hydrogen. Hydrometallurgy. We are going to call this one as hydrometallurgy. Your hydrogen can be used for reducing certain oxides of metals into their metallic form. So that is the ability of your hydrogen, is showing its similarity with your alkali metal. And the next one, differences what you are going to observe for your hydrogen with your alkali metal. So the first difference what we discussed is existence of your unipositively charged ion. H plus is not at all going to be possible to exist individually because of its smallest size, 1.5 into 10 power minus 3 picometer, whereas the same hydrogen is going to be present in the form of H9O4 plus, that is hydronium ion. H3O plus is going to be existing. We are representing simply H3O plus. Originally it is going to be H9O4 plus is the original state of existence of H plus ion in water, and that is the difference we have discussed. And the next one is nature of halides. Nature of halides, when you are going to discuss, this is going to be HCl is a covalent in nature, whereas NaCl formed by sodium is going to be ionic in nature, whereas the HCl existing in gaseous state, whereas NaCl is existing in solid state. So these are the differences are making hydrogen not supposed to be kept along with your alkali metals. And one more point is ionization enthalpy. So what is ionization enthalpy? Ionization enthalpy of your alkali metals is going to be very low, whereas hydrogen is going to be require 13-12 kilojoules energy. How much energy is required to remove the electron from your hydrogen? It requires 13-12 kilojoules of energy is required to make the electron to be removed from your hydrogen. I think everyone knows the definition of ionization enthalpy. What is ionization enthalpy? The minimum amount of energy required to remove an electron, most loosely bound electron, from its isolated gaseous atomic state. So that isolated gaseous atomic state, the electron to be removed, how much energy we are going to supply, that energy is called as ionization enthalpy. The ionization enthalpy required for the hydrogen is going to be 13-12 kilojoules of energy. Whereas if you are taking your sodium or lithium or your any of the alkali metal, they are not having more than 500 kilojoules of energy, half of hydrogen. So that much very less ionization enthalpies are going to be required for the removal of electron from your alkali metals, whereas hydrogen require huge amount of energy to remove the electron from its isolated gaseous state. So these are the differences we are going to have for your alkali metals with hydrogen. The next we will be discussing about how halogens are showing the similarities and the differences. So next one is going to be similarities with halogens. Again, same thing, electronic configuration. Hydrogen is going to show 1s1, fluorine 1s2, 2s2, 2p5. Chlorine will be showing 1s2, 2s2, 2p6, 3s2, 3p5. Now, how many electrons are required for a particular element to reach its noble gas configuration? For this one, what is the nearest noble gas? Helium. For this one, neon. For this one, it's argon. So, hydrogen is also one electron short. Fluorine is also one electron short, and your chlorine is also one electron short. Now, when we are going to take, your hydrogen is also one electron away from the noble gas configuration. Your fluorine and chlorine is also one electron away from the noble gas configuration. So, this is what the similarity we can able to say. The electronic configuration of your hydrogen is like that of your halogens, because halogens also one electron away from the noble gas configuration, nearest noble gas configuration, and your hydrogen is also one electron away from the noble gas configuration. That's why we can able to say they are going to have similarity in their electronic configuration. And next one is going to be oxidation state. What is the oxidation state shown by your hydrogen? +1, like that of we discussed, and your fluorine we are going to have -1, chlorine is also showing the -1, your hydrogen is also showing -1. What are the examples you can take? We are saying, for example, NaF, NaCl, all of them are showing the -1. Here, hydrogen, when I am going to take NaH, sodium hydride, it is going to have -1 oxidation state. What is the oxidation state of hydrogen? In case of metal hydrides, CaH2. What is the oxidation state? Hydrogen -1. So, oxidation state of your hydrogen can able to show -1, which is similar to your halogens. It is also showing the same thing we can discuss in electrochemical nature. In electrochemistry, we are going to discuss regarding, based on the oxidation state or based on the polarity the ion is going to get, that is going to be deciding to which side of the electrode that has to be moved. So now, when I am going to take your chlorides or fluorides, where they are going to be entering into the electrochemical cell or electrolytic cell, as they are having negatively charged F minus, Cl minus, Br minus, all they are going to be moving towards the anode. Anions will be moving towards the anode, and there they are going to be get anode. What is going to be happen? Oxidation, so that they are going to be forming F2 at anode. They will be liberating as F2 gas at anode. In the same way, your sodium hydride, if you are going to take, you will be getting Na plus and H minus. So this H minus also moving toward the anode. At anode, this H minus is going to be forming the H2 gas. So what you can able to see the electrochemical nature, whenever we are going to see the polarity of the ion, that is going to be deciding factor where that ion has to move. So that ions are going to be moving towards the anode. In case of electrolytic cell, when you are going to take, all your halides are going to have uniform negatively charged. So that uni-negative charge is making them to move towards your anode. And at anode, they are going to be liberating as their F2 gas, Cl2 gas, Br2 gas. In the same way, when I am going to take a salt hydrates or ionic hydrates, these ionic hydrates are going to be divided as Na plus and H minus. Now the H minus is going to be negatively charged. That's why this negatively charged H minus is going toward the anode, and then it is going to be liberating as H2 gas. So this is going to be the similarity which is shown like that of halogen. Like that of halogen, it is going to show the similarity, that is going to be the electrochemical nature. Is it clear? And next what we are going to have is one more similarity when we are going to take reactivity with non-metals, reactivity with metals. So when I am going to take reactivity with the metals, when you are going to take sodium plus chlorine is going to give sodium chloride, isn't it? 2Na plus Cl2 gives rise to sodium chloride we are going to get, they are going to form, whereas the Na plus H2 is going to form NaH, sodium hydride. So how the halogens are reacting with a metal? In the same way, calcium with chlorine, CaCl2, whereas calcium with hydrogen, CaH2, calcium hydride. So how the halogens are reacting with a metal? In the same way our hydrogen is also going to be reacting. So that's what the similarity we can able to say. And one more similarity we are going to have is with non-metals. With non-metals also, the reactivity when you are going to compare, they are going to show. Say for example, carbon with chlorine. So what you are going to get? CCl4 it is going to be forming. Same C with hydrogen, we can able to get CH4. We are able to get CH4. So C and the chlorine is going to give CCl4, and C and H2 is going to give CH4, and silicon is also going to show SiCl4, SiH4. So how the metal and non-metals are going to be reacting, the same way the hydrogen is also going to be reacting like that of halogen. So these are all the similarities we can able to say. The hydrogen can be kept along with halogen, can be kept along with halogen. And the next one, the dissimilarities what we are going to have. What dissimilarities we are having? The hydrogen not to be kept along with your halogen. So what is the first one what you can able to say? The first difference is nothing but H minus is not going to be usual, the existence. It's very rare. So we are having the possibility of formation of H minus, but H minus existence is not going to be rare. So it is not going to be present. So it is very rarely we are going to get it. But all your halide ions, F minus, Cl minus, Br minus, they are all going to be present usually. So they are not going to have any problem. But the existence of H minus is not going to be that much normal. We are supposed to get at abnormal conditions only. So that is the one we are going to have. And the formation of that negatively charged gases, what we discussed the electrochemical nature, this is going to be seen usually with when metallic hydrates are going to be. But usually hydrogen is always going to be forming at cathode only. H2 gas is going to be liberated at cathode. It is not going to be possible at anode. So that is also one of the things we are going to have. And ionization enthalpy is similar. So how we are having the halogens will have ionization enthalpy around 1200 and 1300. Your hydrogen is also showing the 1300 kilojoules. That is going to be the similarity we are going to have. But what the difference we are having? The existence of H minus is not going to be usual, and also the H2 gas liberation at anode is also not usual. It is going to be very normally we are going to see H2 gas at cathode only, not at anode. So these differences are making hydrogen not to be kept along with halogens. So finally, where you have to place the position of hydrogen? The hydrogen can't be kept along with alkali metals, can't be kept along with your halogens. So we have to place the hydrogen unique. So every time if you want to see the periodic table, hydrogen is going to be kept separately as one place in the middle of the periodic table as a unique place they are given for the hydrogen. That's why the position of hydrogen we are supposed to be given as center of the periodic table we are going to place it. But along with first period only we are going to place, but we are not placing in along with alkali metals, we are not placing along with halogens, we are going to be placing that hydrogen at the center of the periodic table. That is what the way we discussed now, the similarities and dissimilarities which is showing by the hydrogen. Is it clear? The position of the hydrogen, the forms of hydrogen and the preparations we will see tomorrow class. And all students should suppose to read the NCERT textbook for the hydrogen lesson. You can go through the NCERT textbook. What are the doubts you are getting, you can ask us. So don't get deviated. You are supposed to be get self-motivated. And when we are having the study hour, you can ask us the doubts. Thank you everyone.